know. Our next speaker is Laura Barisoni, and she is going to talk about podocytopathies. Laura, the same applies to you. We are trying to make 25-minute talks.
Okay.
Thank you.
So let me find it. All right. So we are going to talk about podocytopathies very dangerously. We go from conventional morphology to propose new approaches. What are podocytopathies? Those are the definition is proteinuria disease in which pathologic processes arise from intrinsic or extrinsic primary podocyte injury, and where podocyte genotype or phenotype is altered. The common denominator for podocytopathy is fructose deficient, and this is where we always focus diagnostically. Is there fructose deficient, how much it is, etc. What I want to do is go over the evolutionary classification of these diseases, from morphology-based classification, etiology-based classification, morphomic taxonomies, and again, going back to the integrated individual profile phenotype, and how we move, doing that, we move from light microscopy to digital pathology. So my talk is a little bit linked to what I talked about earlier today. So if we look at the history of podocytopathies, we see that in the 70s, the pathology classification really reflected the clinical classification. So one patient had Nephrotic syndrome, had a biopsy, had two choices. No segmental sclerosis and effacement, that was minimal change disease, generally good prognosis, but not always. Or they had the diagnosis of focal segmental glomerulosclerosis. That was it, right? In that, focal segmental glomerulosclerosis was defined originally as a non-proliferative, non-immune complex or complement-mediated disease with poor prognosis and poor response to steroid therapy. Now, in the 90s and 80s, 90s, new morphologic patterns were described, and they were all put together under the umbrella of FSGS. So under the umbrella of FSGS, we have lesion, that we name tip lesion, where the damage is at the tip of the glomerulus. We have lesion of solidification of top at the hilum, or in a non-otherwise specified location of the glomerulus, but also proliferative lesions, such as cellular lesion and collapsing, were all included in the FSGS umbrella. And the work that David Thomas has done has shown that actually this classification has some prognostic features. So if you have minimal change disease or tip lesion, you do fine, but if you have collapsing, you do worse. The problem is, and it's not only limited to this classification, morphologic classification in general carry a lot of limitation. In the case of podocytopathy, for example, the morphologic classification doesn't tell us what is the cause of effacement. And we know that there are multiple reasons why podocytes are damaged and undergo effacement. And in the interest of time, I will not go over all of them. The morphologic classification also doesn't tell us who is going to respond to the therapy, because all these FSGS have, you have five chances. You have tip, you have periodic, but in reality, none of them tells us who is going to respond to conventional therapy, to alternative therapy, etc. Also, the morphologic classification doesn't reflect the molecular profile at all, and neither the genetic background, whether it's a monogenetic disorder or a genetic predisposition. The morphologic classification also doesn't tell us who is going to progress or not. We know that by morphologic classification, we have some glomerular lesion. The status of the podocyte is not really addressed in our classification system because we use only 5 parameters to classify patients: tip, cellular, collapsing, periolar, and NOS. And so we don't know who is going to progress. So when there is a sublethal lesion versus a reversible lesion, when the sublethal lesion becomes a lethal injury, and whether there is failure to repair or failure to protect, and when there is an opportunity for restoration of podocytes versus complete failure to repair. So we don't gain all this information that we need to tell something about our patient. Also, we know that podocytes react in different ways. So we generally accept the fact that if there is a podocytopathy, it's because podocytes get injured. But some get injured and undergo an arrest at re-enter the cycle and undergo arrest at the G2 checkpoint. But others actually overreach this checkpoint and undergo apoptosis. And then when you have apoptosis, what happens then? Well, different things can happen. In some of the cases, you just lose your podocyte and you have a scar. Those are the cases where there is a failure to repair from the parietal cells that come and try to be podocyte repair or damage. In other cases, we know now that there is an exuberant attempt to repair, and in this results in exuberant number of cells that are all the parietal cells that try to be podocytes again. So that's why all our biopsies look different. Some have more similarity than others, etc. What we don't know is, however, when is happening and in any specific case. We also know that there are over 40 different genes that have been identified as cause of proteinuria. And none of them have a very specific association with any of the conventional morphologic features. And we also know that there is extreme heterogeneity. So the same morphologic phenotype results from different genetic background. And at the same time, the same monogenetic defect can present morphologically with a very heterogeneous pattern. So WT1 can present as collapse, as minimal change disease, as segmental sclerosis, etc. So later on, we said, well, we need to have a little bit more than a monolayer of information to classify patients. So why don't we try at least to add the etiology? So we propose a taxonomy of the podocytopathies that is based on morphology on one side, defined by pattern of glomerular injury and podocyte epithelial, and the number of epithelial cells in the urinary space, and etiology as idiopathic, genetic, and reactive. And according to this proposal, we have four broad classes. We have minimal change disease, when we have normal number of podocytes and no changes by morphology. We have segmental sclerosis, where we have solidification of the top and decreased number of podocytes. And we have collapse that is now separate from FSGS. It's not an FSGS, in my opinion, where there is an exuberant number of epithelial cells and wrinkling unfolding of the glomerulus membrane. Actually, these two look quite different. And also, we included diffuse mesangial sclerosis that is characterized by mesangial expansion, but also an increased number of podocytes. So, and in our proposal now we have a table that we can use and has two variables, but we can start using, because in this taxonomy, each patient will have a very specific cell at their place, because each of these taxons are mutually exclusive. So you can have a patient with a specific genetic disorder and a specific pattern of injury, which is either FSGS or collapsing, and will be placed either here or here. But also we can use taxonomy as a framework to start thinking about therapy, right? We don't want to treat this patient as we treat this ones. So if we realize this is a reactive one, we want to think about before using the strong immunosuppressive therapy and rather target the underlying condition. However, this is, I think, it's a progress, but we're not there yet. And the classification of podocytopathies is still evolving. And we have to put together genetic, molecular, morphologic data and consider the heterogeneity of all these and how do we put them together. And we're going back a little bit to the concept that I discussed this morning. So there are a lot of lesions, for example, that are named FSGS. It's extremely heterogeneous. But also there is extreme heterogeneity in the podocyte injury. We are accustomed to comment on food process effacement, and people ask us, so if the food process effacement is 50% or 60%, and that's about it, like it will be the answer to the treatment, right? But podocytes react really in multiple ways, not only for process effacement, but also we notice that in some cases there is extreme reorganization of the actin base cytoskeleton. Some other patient has extreme macrovillous transformation compared to others, or detachment from the podocyte from the underlying disease. And in other cases, you have not only loss of food processes, but also loss of the primary processes, and the cell body sits directly on top of the glomerular basement membrane. Also, let's think about FSGS, and we hear still a lot of people talking about primary versus secondary FSGS. And what is secondary FSGS? We assume that, for example, if the glomeruli are bigger than what expected, indeed the segmental sclerosis is pretty much the same. This is secondary post-adaptive FSGS. But in reality, are we really not treating those patients? Are we really not looking at those patients for the molecular profile? Because it has also been shown, for example, that many of these patients have an underlying genetic condition. So I think that if we diagnose secondary FSGS, we're really not done there. And if we keep on diagnosing secondary FSGS, we really prevent people from going a step farther and find out what this patient really has. And for example, in many of these patients who are obese, but not every obese has FSGS, the endocrine status may play as a cofactor. So, but the point is that I don't think we can simplify as, obesity-associated FSGS, because if that was real, all the obese people in America will have a renal biopsy, and we don't. So, insights were made by investigators who look at the microRNA gene expression in non-genetic FSGS. And that actually was very helpful because they could identify some microRNAs, such as microRNA 193A, that they were increased in some conditions that were not genetic. Also, other investigators in China has discovered that the microRNAs can also be used not only to detect or to prove the activity in FSGS, but also to monitor the disease activity. So they found that microRNA 125B and 186 and 193A were increased in FSGS, but 125B and 186 were lower in patients with remission. And 186 also correlated with the degree of proteinuria. So now we have some sort of biomarker that can help us in non-genetic FSGS to figure out what is happening. And indeed, if we think about all the observations that we made over the last 20 years about podocytes, indeed they help us to understand this disease a lot better. For example, studying the role of microRNA, we can understand certain pathways and things that happen not only in FSGS, but also in other diseases. And looking at all the discoveries that we have made on podocyte protein, it really helps us to understand why in some cases patients respond to one therapy versus another. So we don't want to discard all this. It certainly is important. If you look at the literature, and if you look at people who look for a biomarker for FSGS, you will find like 20 papers. Everybody has a biomarker. And in reality, everybody is right. The fact is that we are dealing with a very heterogeneous group of diseases. So we can find more than one biomarker. What is the point? The point is that we really need, and we need to go back to what I was talking this morning, a multi-level analysis. A very we call FSGS a bunch of diseases. And we have to do a multi-level analysis approach and integrate the structural changes with the clinical and with all the other information that we can obtain to establish clinically relevant patient categorization, because we know that each individual clinical phenotype is the result of genetic variation, epigenetic modulation, transcriptional regulation, protein function, metabolomic, and also what happens at the structural level. So we need a multi-level analysis. So as pathologists, we need to change the way we do things. And currently, pathologists create disease categories. We create, not artificially, but we create disease categories, and then we test them against the outcome. But our disease categories are created based on few selected parameters. And so we need to switch from this model to integrated pathology, where there is an unsupervised learning and multi-Excel data set defining the category of patients with similar biological trajectory. So this is very different. It's not us deciding what is important, is what is on the slides and what is on the data, deciding how we classify the patients. And that will help us to predict clinical outcome and identify targets for therapeutic intervention. So we're going back, so how did we do that? How did we approach that in the setting of podocytopathies? So I already went through these slides earlier today, but we use a different approach. Instead of deciding upfront what is important, 5 categories, 5 parameters, and give a quantitative diagnosis, we collected the data on individual structural changes in a very agnostic way. And by collecting this data, now we have a data set that we can use, and we can let the data tell us what the classification is. Again, this is a very comprehensive system, so we have multiple parameters, not only the 5 parameters or 6 parameters that make us classify minimal change disease and FSGS. We look at status of the endothelium, we look at things other than food process effacement, but also other histologic parameters. Briefly, the next-gen scoring system that now has been actually implemented also in other consortia has good reproducibility data, and this is number one thing, right? We have to, every time we do a classification, it has to be reproducible, or have some reproducibility, because otherwise we will never capture data that are relevant worldwide. And so we tested for some commonly used tubulointerstitial descriptors. We had excellent reproducibility. If you look at some of the ultrastructural descriptors, this is just 4 of the 16 that we have. We had excellent reproducibility for the parameters that are commonly used in renal pathology, but such as food process effacement. When we look at condensation of the actin base cytoskeleton or microvillus transformation, it was a little bit less. For the glomerular descriptors, the 1A statistic showed a good excellent concordance in 79% of the descriptors. We also noticed that the more we train people in the webinar training, the more our reproducibility increases. So the fact that we have digital pathology is actually helping us to do that. And if we don't have good reproducibility, what do? Can we use those parameters? Well, we noticed that if we group them by similarities, the reproducibility increases. So podocyte hypertrophy, podocyte hyperplasia, well, maybe we're not great when we do that, but if we say, is there podocyte hypertrophy and hyperplasia, then we have good reproducibility, then we can use that parameter. And concordance, was independent from years of experience. And that makes sense, because years of experience teaches you how to interpret a biopsy, but fellows are taught how to recognize the individual structural changes. So once we taught people how to score for the individual structural changes, it didn't matter how many years they practiced pathology. So, can descriptor-driven patient categorization predict outcomes? So what do we do with this data? Can we do something that is useful clinically? So instead of pre-selecting the parameters that are important for outcome, we let the computer cluster our patient based on common descriptors. And so we did a patient cluster analysis using all the descriptors available. And we found five cluster of patients here. In this heat map, we have represented all the descriptors and the clusters. And the darker is the bar, the more frequent a descriptor was present for that cluster. And when we look at the outcome, we see that these 5 cluster of patients have different outcomes. So it's clinically relevant, as well as different remission to proteinuria. So they are predicting what is happening to the patient. And surprise, surprise, when we look at whether they overlap with conventional classification system, they don't. So here is your clusters, but minima change disease goes with any of these clusters, those who do well and those who don't do well. The NOS does the same, the tip lesion does the same, etc.
Ooh, it's time, that's why.
Oh my goodness. So we repeated the same experiment using only the histology features, and we eliminated the electron microscopy features. We more or less find the same thing. Conventional classification systems are based only on glomerular parameters. They completely exclude everything else that is happening in the kidney. So we said, like, why don't we compare glomerular descriptors to conventional classification system? But again, there was no overlap, and yet the cluster that we found were clinically significant. I want to show this picture for a reason. Sorry, I have 3 more. So we look at the electron microscopy descriptor alone, and we did a patient cluster analysis. And again, we found our heat map and our outcome and remission, no overlap. But what is important here that I really want to show is that we always think that food process effacement is critical. In reality, when we look at what drives the clusters, all these parameters with an asterisk are driving the cluster. Not only food process effacement, but also parameters as condensation of the actin-based cytoskeleton, the status of the epithelium, etc., etc. And when we look at which descriptors drive outcome and remission, actually macrovillus transformation and loss of endothelial fenestration were the ones driving outcome and remission, and not food process effacement. Let's go. Okay. So the next question is, okay, you use the descriptor, you let the computer put together the cluster of patients with common features, but can quantifiable structural changes also predict molecular mechanisms? Is it relevant clinically? Yes. Is it relevant to predict what is altered? Because if I know what is altered in a cluster versus another, I can treat that cluster with a specific therapy that is different from the one that I use for the other cluster. So comparing glomerular gene expression profile from cluster 1 and 2 using only the glomerular descriptor, we found 207 significantly differentially expressed genes. And functional analysis reveal enrichment of several canonical pathways and biological processes that reflected activation of inflammatory and innate immunity pathway. We also found 100 genes that were associated with 6 descriptors or group of descriptors. And if you look at this list, most of these descriptors are not included in conventional classification system. So without doing this granular analysis And quantitative analysis will miss the correlation between certain features and certain genes. So if you use the conventional classification system that doesn't discriminate whether you have global sclerosis or not, doesn't discriminate if you have amyloidosis or not, you will miss this information. So this is my last slide. So we need a computational integration of morphomic data to better define glomerular disease, and we need to take into account clinical phenotype, quantitative morphology, protein cytokine from serum urine, transcriptional data, epigenetic signature, and genetic variation, and integrate them along a genotype-phenotype continuum so we can better define disease mechanism in regulatory pathways and network, define functional homogeneous subtypes to better predict outcome and identify target for therapeutic intervention. Thank you.
Thank you, Laura. Thank you very much for bringing us into the future and also speaking perfect Greek. I can find Barisoni